In this section, I'll be going over pairs of Platonic solids and doing a more in-depth analysis and compare the geometries, the various axes of these different Platonic solids, and see how they align with each other. I'll be using some various models to do so. You've seen these earlier. These are the spherical Platonic solids you saw earlier. This is similar, but it's a shell overlay that will basically allow me to overlay two different geometries and compare them. And in addition, I'll introduce what I call a polydesic, which basically takes an edge of the spherical polygon and projects it down into the center. And these can be taken apart section by section, and they can be interchanged between the Platonic solids to compare their geometries as well. So let's compare the geometry of a spherical tetrahedron and a spherical cube. What we have here is a spherical tetrahedron placed inside a shell of a spherical cube. We can see the axes have lined up in certain ways. We have the vertices of a cube lining up with the face of a tetrahedron in some cases. In other cases, the vertices of the cube lines up with the vertices of the tetrahedron. In addition, you can see that the edge axis lines up with a face of the cube, and that edge of the tetrahedron divides that square face into two halves. We saw earlier that the face of the cube is equal to 2 pi over 3, so each of these sections are equal to pi over 3. Let me show this another way. If we take this spherical cube, take out one of the sections, one of the faces, and that can be replaced with the face that basically has been divided into two. Now we can actually take three of these and rearrange them to make the face of a tetrahedron. And as you can see, it's a perfect fit in the tetrahedron right here with a surface area of pi. And now we'll compare a tetrahedron and a octahedron using the similar models that you saw earlier, and we'll be using a shell of a spherical tetrahedron and overlay that with a spherical octahedron. So what we have here is a spherical octahedron placed inside the shell of a spherical tetrahedron. And let's look at some of the alignments. You see the vertices of a tetrahedron lines up in some cases with the face of the octahedron. You also have the face of the octahedron lining up with the face of the tetrahedron. You'll also see that an edge axis lines up of the tetrahedron with that of the octahedron. And you'll see that the edges here of the tetrahedron divides up that face of a octahedron into three equal sections. In the earlier section you saw that the face area of the octahedron is pi over 2, which make these subsections of the pi over 6, which I can show in this other model a little more clearly. So if we take one of these sections out that is equal to pi over 2, replace it with a section that's been already subdivided into three sections, each of which is equal to pi over 6. This also now can be arranged by adding in three other subsections and arranging them this way. And that now makes a face of a tetrahedron, as you can see fits in this model here. And these six subsections, each having an area of pi over 6, adds up to the face area of a tetrahedron, which is equal to pi. So now we'll compare the geometries of the cube and the dodecahedron. Again, we'll be using similar models we saw earlier, where I can take an overlay and compare the geometries of a spherical cube and a spherical dodecahedron. So here we have a spherical dodecahedron inside the shell of a spherical cube, and we look at how the axes align between the two. We have the face axis of a cube lining up with the edge axis of a dodecahedron. In addition, we have the vertices of the spherical cube also lining up with the vertices of a dodecahedron. And then we have an interesting division of the face of the spherical cube by the edges of the dodecahedron. From an area perspective, we know that the face area of the cube is equal to 2 pi over 3, whereas the face area of the dodecahedron is equal to pi over 3, 1/2 the area of the cube. This can be shown a little more clearly with this model, where we can take the face of the dodecahedron and we can see this is divided up by the edge here of the cube. We can take two of these and rearrange the subsections that will create the face of the cube, which has twice the area of that of the spherical dodecahedron. In this comparison, we'll be looking at the spherical octahedron and the dodecahedron and comparing their geometric properties. I'll be using an overlay similar as before to look out that the axes line up between these two spherical polygons. So what we have here is a spherical dodecahedron placed inside the shell of the spherical octahedron. Now let's take a look how the axes lined up. You can see that the face of the spherical octahedron lines up with the vertices of the dodecahedron. In addition, you can see that the vertex of the spherical octahedron lines up with the edge of the spherical dodecahedron. And you can also see that the edge of a spherical octahedron divides the face of a dodecahedron into two equal subsections. The face of the dodecahedron equals pi over 3, so the two subsections equal pi over 6. Let me demonstrate this a little further in the other models. So if we take the spherical dodecahedron, you can see that this face can be replaced with a section with two equal subsections, again pi over 6 each. These same subsections, 3 of them, could be arranged in this pattern here, and now that will fit in to the face of an octahedron that we know is pi over 2, which is confirmed by the fact that 3 times pi over 6 is equal to 1/2 as well. So now let's look at the comparison between the icosahedron and the octahedron. We'll be using similar spherical models. And again, we'll be using an overlay that could be dropped on top of the spherical icosahedron and do the axis comparison. So here we have the spherical icosahedron inside a shell of a spherical octahedron. And let's just look at some of the axis alignments. You can see that the vertex of the icosahedron lines up with the edge axis of the icosahedron. We've got the face of a octahedron also lining up with the face of a icosahedron. And we can also see that the edge of the octahedron divides up the face of the icosahedron into two equal subsections. We know that the face of the icosahedron is equal to pi over 5, so those two subsections will equal to pi over 10 each. Let me show you that in this other model. Here we have another version of a spherical icosahedron. take out a subsection, which is equal to pi over 5. And that could be replaced by a section that has two sections that are pi over 10 each. This same subsection can also be basically rearranged by using three other subsections aligned like this. So in total we have 5 subsections for a total of 5 pi over 10, or pi over 2. And then that's a perfect fit to fit inside the face of a spherical octahedron. So I came across this interesting relationship between these 3 spherical platonics that both have triangular faces: the spherical tetrahedron, the spherical octahedron, and the spherical icosahedron. Now there is a special relationship between the size and orientation of these 3 triangles that I can more clearly show using these other polydesic models. Here we know that the face of a spherical tetrahedron has a face area of pi. I showed earlier how we can take 2 faces of a spherical octahedron and use the subsections and rearrange them to create the face of a tetrahedron. So you can see that actually fits in here perfectly. We can take this one step further. As I showed in the previous video, we can take sections of a icosahedron and arrange it in such a pattern that fits in perfectly on top of the face of the spherical octahedron. And now you can see the specific arrangements of each triangular face, how they fit in there. And I can show you this in more detail on the following slide. This diagram here illustrates the face of a spherical tetrahedron here in red, showing its area of pi, as well as its internal angles of 2 pi over 3. If we overlay the face of the spherical octahedron here in green, this illustrates how the area is divided up into nice simple fractions of pi, as well as all the internal spherical angles end up being nice simple fractions of pi. And finally, if we overlay the face of the spherical icosahedron here in blue, it as well continues subdividing the area into nice simple fractions of pi, and notice the same simple fractions of pi that describe the internal spherical angles. Just thought this was a nice, clean relationship. So let me demonstrate how we can start with a spherical tetrahedron and slowly evolve it by adding in bits and pieces of other spherical platonics and integrate all together to form another spherical structure. If you recall in an earlier video, you can take the face of a spherical cube, divide that into 2 subsections, and these 3 of them could be rearranged to create a face of a tetrahedron. Let me put that in. I'll take another similar face, integrate that into the structure. So now this consists of components of a spherical cube as well as the spherical tetrahedron. Again, you saw earlier how I could take pieces of a spherical octahedron and rearrange its subsections to create another face of a spherical tetrahedron. Let me integrate that in. We'll do the same thing on the other side. And now we have a structure. We can add bits and pieces from a spherical octahedron and a spherical cube. Now we can take the original section of a spherical cube and reincorporate that into the structure. And as well, as you saw from a previous video, you can take bits and pieces of a spherical dodecahedron and arrange them into a face of a spherical octahedron. Basically now we've incorporated bits and pieces of all the Platonic solids into one structure. Now let's look at the duality between the spherical Platonic solids. Here we have a spherical tetrahedron inside the shell of another spherical tetrahedron. The axis of the face and vertices line up, as you can see here. And we also see that the edges of the axis stay aligned, but now they're orthogonal to each other. If we look at the duality between the cube and the octahedron, here we have a spherical cube inside the shell of a spherical octahedron. Again, we can see the vertices of the spherical cube lining up to the face of the octahedron, as well as the vertices of the octahedron lining up the face of the cube. And again, the edges are aligned but orthogonal to each other. Similarly, here we have a spherical dodecahedron inside the shell of a spherical icosahedron, and we have the vertices of the icosahedron lining up with the face of the dodecahedron, and the vertices of the dodecahedron lining up with the face of the icosahedron, and the edges line up, but they're orthogonal to each other as well.